All right. Okay. So going ahead, the next topic in this vector differentiation is called as the scalar and vector point functions. Okay. So this is called as scalar and vector point functions. Right. Now let us say that we have a point denoted by x comma y comma z in any given region. All right. So let's write that first. If every point, that is x comma y comma z, of a given region, right? Let's denote that region by capital R. So what do you mean by this capital R? This capital R represents, maybe it can be a curve, okay, or it can be a surface area, it can be a volume, right? Anything, right? So let's say that it is denoted by capital R in space, right? Corresponds to what is called as a scalar function. In the sense, it's not a vector, right? It's a point denoted by a scalar function. For example, area is a scalar. All right. So let's try to write it in this fashion. Region R in space corresponds to a scalar function, right? So let's denote that scalar function as phi of x comma y comma z, right? Then this phi, right, is called as scalar point function, right? So normally this scalar function is also referred to as the scalar field, right? For example, let's say that we are trying to represent a given coordinate system. It can be polar coordinate system, it can be rectangular, or many other types of coordinate systems do exist in engineering. And let's say that we try to represent that coordinate system, and using that coordinate system we are trying to represent a area or volume or anything, right? Okay. In such case, let's try to give an example now. So for example, this area could be represented as x square plus y square plus z square. Now you see that this the x square is not being multiplied by I cap, y is not being multiplied by j cap, z is not being multiplied by k cap, right? So because of that reason you can call this as a scalar function. It's not a vector. Let's denote this by using another function. Maybe this is x y square z cube. So whenever you are trying to represent a given particular point x y z, right, given that it is a scalar point, right, you call that kind of function as a scalar field, right? These two are the examples for right, the scalar point function or scalar field. Okay, now let us say there is another version of representing a point, but it is not going to be a scalar now, it's going to be a vector, right? So let's try to write that now. If every point that is x comma y comma z of a region capital R, right? corresponds to say a vector. Now it's not a scalar, okay, it's a vector. Let's denote this is a vector of x comma y comma z, right? If every point on some point, right, every point is being represented by a vector in the given space, then you call that as a vector point function, right? Then the vector A is called as vector point function, or you can definitely call it by the name vector field. Okay, for example, we know this, we already have solved many questions and we use this many times. For example, vector A is equal to x into I cap, maybe, plus y square into z cap plus z cube. My mistake, just a second, I'll just correct this. This is not z cap, this is j cap. Y square into j cap plus z cube into k cap, right? You can see that this particular function what we are writing is, right, a vector. That's why this vector A is called as vector field, or the other name is vector point function. Let me give another example. So this vector A is also equal to, maybe this is x into y into z into I cap plus yz into j cap plus z into k cap. You can see that this is a function now, x into y into z, right? For any given point in space x, y, z, this x into y into z will be a function. So multiply that with I vector, a unit vector along x-axis, I cap, you get a function, plus yz into j cap plus z into k cap. Okay, so because of this reason, right, now you know that we are trying to represent this particular function and we are going to call this as a vector function. All right, now let's proceed further. Right, now what are the different operators that you can apply on either a scalar function or a vector function? Because we know that we have two types of functions defined now, right? Let's define the operators now. Right, first operator, on a scalar you can apply a vector differential operator, or on a vector you can apply a scalar differential operator. These two types are possible, they are allowed and they are valid. Okay, now, so first operator, operator number one, is called as a vector differential operator, that is this particular function denoted as delta, inverted delta. Okay, this is what we call as del operator, right? That is defined in the following fashion: del operator is equal to dou by dou x into I cap plus this is dou by dou y into j cap plus the dou by dou y, my mistake, dou by dou z, because last operator has to be the z axis, that's why this has to be z. All right, dou by dou z into k cap. So you can see that we know that there is a sigma operator, summation. So this can be written as summation dou by dou x into I cap. Okay, so I, in the sense, it can be extended further to all the possible directions. In this case, if you are using a three-dimensional case, this will be I, j and k. That's why in short form you are writing in this way. So this is the first operator that we are going to use. So let's go to the second case. That's the second operator. This is called as the Laplacian operator, right? So this is denoted by del square. So what is a del square? Del square is, it's a double differentiation. Dou square by dou x square plus dou square by dou y square plus this is dou square by dou z square. So in short, we can write the same function. Okay, so that is this del function. Del square is equal to summation of dou square by dou x square, right? So first function, you remember, this is called as a del operator, right, which is operator number one. And then we have operator number two, which is the Laplacian operator denoted by del square. Okay, now let's go ahead. Now how do you apply this, right? These two operators are there, we understand that now. These are the two different operators that can be applied on the scalar and the vector point functions. Fine. Now how do you apply them? So the application of these functions, right, on any given scalar or vector point functions have specific names. Let's call the names specifically. So the first name, right, first operator is called as the gradient. This is called as gradient, gradient of a scalar field, right? If, for example, it says that scalar field should be considered and you should apply a function called as gradient, right? So let's define that. If phi of x comma y comma z is, right, we know that phi is denoting the differentiable scalar function. It's a scalar function. Okay, so phi xyz is a continuously differentiable scalar function, then the gradient of this given function phi, right, it is denoted, it's called as, how do you read this? This function is called as grad of phi or simply grad phi. Okay, so gradient of this function phi is denoted by, this is del phi, or you can read it as the gradient phi. So how do you read this? So del phi, or you can call this as, some of the textbooks will denote this using this notation. This is grad phi, both are same. Okay, so del phi or grad phi is nothing but, so apply the function. So we already know that what is a del operator. You can go back and check that what is a del function. Del is nothing but dou by dou x, right, into I cap. But you are applying this del operator to a specific function called phi. So how do you denote this? So this has to be dou by dou x into I cap is the del function, right? But there has to be a function applicable which is phi. So plus this is dou phi by dou y into j cap plus dou phi by dou z into k cap. Okay, so since you are differentiating and multiplying by I, j and k with respective axis, so the result is this grad phi or del phi is the, I'll write, result is a vector quantity. So you understand one point here. I'm actually I'm taking a scalar function, that is this phi. So phi is a scalar function, but when you apply the gradient to that particular function phi, the result is going to be a vector quantity. Why? Because you are multiplying by I, j and k. Phi is scalar, so dou phi by dou x is a scalar, but when you multiply by I, this becomes a vector. So we define the first function, which is called as the gradient of a scalar field. So let's go ahead to the second function. This is called as divergence of a vector field. Right, now you see that it says that you are using a vector field and applying a particular function called divergence, right, to get some answer. All right, so let's try to give a notation for this first so that we can extend this to an application. All right, so that is, if let's say a vector, right, a vector at a point x comma y comma z, this is continuously differentiable. It's a differentiable vector function. It's a vector function. Then the divergence is a name given. Okay, divergence of a vector, right? You see that this is called as div of a vector, right? So is, this is del dot, you see that there is a dot in the middle, this is del, not simply del phi, this is del dot a vector. Divergence is defined, the divergence of a vector a is defined as del dot a vector. So compare this to the previous equation, you can see that this is del phi, gradient of a scalar, del phi, gradient of a sorry, not a gradient, divergence of a vector is del dot a. Let's try to give a notation for this now, right? This is what is a standard way of representing, but let's try to give a mathematical notation to this, right? That is, if, let's give a notation for a vector first. So let's say that this is a1 into I cap plus a2 into j cap plus a3 into k cap. We know that if we try to represent a given vector in this notation, a1 comma a2 comma a3 are the functions of x and y and z, right? We know this. Anyway, let me write that. A1 comma a2 comma a3, they are functions of x comma y comma z. All right, in this case, let's try to give a notation now, that is div a vector. So how do you call this? This is del dot a vector. Anyway, let me write this once again. So this is equal to del dot a vector. So how do you write a del dot a vector? This is nothing but, what is a del? Del is dou by dou x into I cap, dou by dou y into j cap plus dou by dou z into k cap. This is del dot, let me write the a vector below this. This is a1 I cap, a2 j cap plus a3 k cap. Now we see that this is a dot product. I can apply the dou by dou x to the term containing I only, right? So this implies the del dot a vector is equal to, there is a dot product that has to be denoted. I cannot neglect that. This is equal to, now we apply. So this is dou by dou x into a1 plus this is dou by dou y a2 plus dou by dou z into a3, because I can only multiply I into I, right? I into I is 1. Dou by dou x should be applicable to a1, so that you can multiply I into I, so that you get this term, plus dou by dou y gets multiplied with a2 and dou by dou z gets multiplied with a3. That's why this is the notation. Now you see that in this answer I don't have I, j and k. So this implies, right, the divergence of a vector is, since I don't have I, j, k, right, in my final answer, it's a scalar, because I, j, k represents a vector. When you don't have a I, j or k in your answer, this is a scalar. I need to remember this. So two things to remember so far, whatever we discussed today. Gradient of a scalar gives me a vector answer. At the same time, divergence of a vector gives me a scalar quantity. Alright, then the third important operator which can be applied to the vectors is called as the curl of any given vector. This is the third operator. So how do you denote that? If a vector of x comma y comma z is continuously differentiable vector function, right, then, right, this curl is denoted as curl of a vector. Curl of a vector is, you see the notation, this is del, it's cross, del cross a vector. So first one was del phi was scalar, second option was del dot a, right, and the answer was a, you had a vector input, output was a scalar, but we know that when you take a cross product, our answer will be, right, answer will also be a vector, right? So this is how you try to represent. If vector a is equal to, let's say a1 into I cap plus a2 j cap plus a3 k cap, then curl a vector, that is del cross a vector, right? We know that how to write a cross product. So how do you write a cross product? It is a determinant. Okay, let me write this properly now. So this is equal to, it's a determinant. I know that I have write I, j, k. So since you are applying the differentiation del cross a, that del operator should come first. That is dou by dou x, dou by dou y, and dou by dou z. You are applying this to the second one, that is a vector, which is a1, a2, a3. So how do you represent this now? This is the standard, this is how we remember, but when we apply this, we are going to get the following notation. That is curl A is nothing but, see, this is I cap into, right, dou by dou y of A3 minus dou by dou z of A2 minus j cap into, right, when I take the j cap, I should, right, use dou by dou x of a3 minus dou by dou z of a1. It's a simple simplification of the determinant. All right, so the next term should be plus k cap into dou by dou x into a2 minus dou by dou y into a1. So we try to apply this in the following fashion to get the final answer. Okay, now let's go ahead and use these notations to solve some of these standard problems. Okay, all right. Okay, the first question is this. Question number one is this, all right? If vector A is equal to x square yz times I cap plus y square zx times j cap plus z square xy times k cap, then find the following, that is divergence of A curl A. Okay, so let's try to answer this now one by one. So how do you find out divergence of A vector? So divergence of A is nothing but, look back, this is del dot A vector. So del, in the sense, what is del? You try to substitute. This is dou by dou x I cap plus dou by dou y j cap dou by dou z k cap. This is a del dot. Write the given vector A here. That is x square yz I cap plus, I'll write here, this is y square zx j cap plus z square xy into k cap. In the sense, I am supposed to apply the dou by dou x only to the term containing I in vector A. So to simplify this, now let's apply this. So dou by dou x gets applicable only to this, dou by dou y only to this, dou by dou z only to this. That's what is the meaning of multiplication of I vector or I cap with I cap. So this is equal to, this is, let's write dou by dou x is getting applicable to x square yz plus the next term, that is dou by dou y is being applicable to y square zx, right, plus the last term, that is dou by dou z is being applicable to z square xy. So what's the first term? Differentiation. It's a partial derivative. You see that there is a difference between dou by dou x and d by dx. Okay, dou by dou x is partial differentiation. In the sense, you just look at what is there, what is the term containing x, only differentiate that, leave the other terms as it is. In the sense, x square I differentiate. X square differentiation is 2x. After that I have yz, you write yz as it is. Plus, see the second term say that dou y by dou x, dou by dou y of this term. So differentiate only y term, leave the rest. So this is 2y into zx. Last term 2z into xy. So you can see that all the terms are same. So 2 plus 2 plus 2 is 6. So the answer is 6xyz is the final answer. Okay, then let's go further. So the next part is that find the curl of A. Curl A vector. What is curl A vector? This is del cross A vector. Okay, so this means this is del. Okay, let me write the del operator as it is now, so that we can simplify this further. So this is dou by dou x a cap plus dou by dou y j cap dou by dou z k cap. This cross vector. So what's the vector? This is x square yz I cap y square zx j cap plus z square xy times k cap. So but though we write this in the following fashion, in order to simplify we use a determinant, that is I j k. So this is dou by dou x dou by dou y dou by dou z into the following terms. The terms in the second equation in the sense vector A is x square yz y square zx z square xy. So I am supposed to simplify this determinant now. Okay, so how do you simplify this? Let's write this is I into, that's the first this thing. So I need to perform the following operation: dou by dou y into, this is this and this. So dou by dou y into z square xy. I should apply that first. So this is z square xy xy minus dou by dou z into, this is y square zx. This is the first term, that is I. Second term is minus j cap into, when I write j cap, write this into this and this into this. Standard way of simplifying the given determinant. So this is dou by dou x of z square xy minus dou by dou z of x square yz. Is the second term. Then we'll write the third term. So plus k cap into, so this and this. So simplifying them now, I'm going to get the dou by dou x of y square zx minus dou by dou y of x square yz. Okay, now let's simplify these equations, whatever we have written now. So this is I cap into, see, dou by dou y. So y is only y over there, so differentiation becomes 1. So this becomes z square x minus, so differentiation of this gives y square x. That's the first term. Minus j cap into, differentiation happens with respect to x in the first case, so x cancels out, you have z square y minus z cancels, you have x square y. Then let's go to the third term. So plus, this is k cap into, differentiation happens to with respect to x first, so this is y square z minus, y cancels in the second term, I have x square into z. Alright, so let me try to give a simplified notation now. So this is equal to, see, x is common in the first term, so this is x into z square minus y square into I cap. Then in the second term, this is, I'll write plus, y I'm going to take out. When the minus goes inside, this is x square minus z square into j cap. And the last term is plus, take a z common. When z comes out, this is y square minus x square into k cap. Right, on the left hand side we know that this is del cross a vector. So we found the divergence and curl of the given vector. Okay, now let's go for a function, right? So this is vector A. Vector A is equal to 3x square y z cube into I cap minus 9x y square z to the power 4. This is z to the power 4 j cap plus 12x cube y power 4 into z square into k cap. So the question here is find, this is divergence of a vector and curl of vector A. So we know that the given A vector is as shown here. Now I need to apply, first I need to find the divergence of vector A, that is nothing but the del dot A vector. So when is this del dot A vector? So let's write the del first, that is dou by dou x into I cap plus dou by dou y into j cap plus dou by dou z into k cap. Okay, dot product of this with the vector A. So you can see that vector A is 3x square y z cube into I cap minus 9x y square z to the power 4 j cap plus 12 x cube y to the power 4 z square into k cap. Now we know that we can apply this particular function, right, in such a way that I can be applied with the I itself. So this means, so what's the answer? That is dou by dou x can be applied only to the first term, that is 3x square y z cube. Then plus dou by dou y, this can be applied to the only the second term, that is minus 9x y square z to the 4. Then plus the dou by dou z should be applicable to 12 times x cube y to the 4 z square. Okay, now you can see that this we can apply, right? Simply differentiate. So x is getting differentiate, x square is there, x square differentiation is 2x. So 2 into 3 is 6 x y z cube. You see y and z will not change, y as it is, z as it is. So y is y, z cube is z cube. Only x square becomes 6x. Okay, then next term it is minus, I am differentiating y, so y becomes 2y. So 9 into 2 is 18. So minus 18 x as it is, y square becomes y and z to the power 4. And the last term, if you see, this is plus, I am differentiating only z, right? So there is a z square becomes 2z. So 2 into 12 is 24 x cube y to the 4 into z. This is the final answer, which is divergence of A vector. Okay, and the next part is nothing but I am supposed to apply the curl. right? So this is curl of the given vector A. What is that? That is denoted by del cross A vector. So let's write them now. So this is dou by dou x I cap plus dou by dou y j cap plus dou by dou z into k cap dot, this is vector A. So let's just look at what was the A vector A. This is 3x square yz cube. So this is 3x square yz cube I cap, and the next term is minus 9x y square z power 4 minus 9x square y z to the power 4. Is it? No, xy square z to the power 4. Sorry, let me correct this. This is x y square z to the 4 j cap, and the last term is 12 x cube y to the 4 z square. 12 into, this is x cube y to the 4 x cube y to the 4 z square into k cap. So this is what we want to do. It's not a dot product, it's a cross product. So how do you take a cross product of two vectors? This is equal to I j k dou by dou x dou by dou y dou by dou z, and the terms below you write like this. This is 3x square y z cube minus 9x y square z to the 4. So this is 12x cube y to the 4 z square determinant. Alright, so this is, now we are applying the determinant now. So this is I cap into dou by dou y of 12 x cube y to the 4 z square, that is this into this minus this into this. This is how I should apply. So next term there is a minus of minus, so this becomes positive. So plus dou by dou z of 9x square, sorry, 9x into y square into z to the 4. This is the first term. Then minus j cap into, now what do you do, this into this, this into this. Okay, so let us apply this. So this results in the following answer. So minus j cap into, this is dou by dou x into 12x cube y to the 4 z square minus dou by dou z into 3x square y z cube. Okay, that's this, plus k cap into, when you multiply this into this and this into this. Okay, so because of that, now we are writing, this is dou by dou x into dou by dou x into minus 9x y square z to the 4 minus dou by dou y into, this is 3x square y z cube. Right, this is the simplification of the above said determinant. Now when we simplify this, we are going to get the following answer. So this is equal to I cap into, the differentiation happens with respect to y in the first term. So there is 4y cube. So 12 into 4, 48. 48. This is x. X remains as it is, x cube. Y's power will be reduced. So this is y. 4 becomes 3, z square. Okay, then the second term differentiation happens with respect to z. So z to the 4 becomes z to the 3. So 4 will come down. So this is plus 9 into 4, 36 x y square z cube. This is the first term. Okay, then let's apply minus j into j into. So differentiation happens with respect to x first. So this is 36 x cube y to y cube z square. Then differentiation happens with respect to z. So that is 3 into 3, that is 9 into x square into y z square. And the last term is plus k cap into, differentiation happens with respect to x. So x differentiation is 1. So this is simply minus 9. Sorry, there is no x now. X is vanished because there was only one x, and when you differentiate, this becomes like this. So this is minus 9 into, this is minus 9 y square z to the 4 minus differentiation with respect to y. So y vanishes. This is 9. Is it 9? Sorry, it's just 3. My mistake. So this is minus 3 into x square z cube. All right, so this is the final answer. So you can solve it in this fashion and get the answer, which is nothing but the curl of the given vector. So whatever we studied earlier, we have proved that now, which means if you have a scalar and apply the first operator, right? The first operator is nothing but gradient, right? Gradient, when you apply to a scalar, the answer is a vector. That's what we verified. And the second thing also we verified now, that is divergence of a vector field is going to be a scalar. And the last part we verified now is curl, if you apply to a vector, the answer is also going to be a vector. So we can just verify now whatever answer we got just now here. So you can see that we had some vector, we applied a curl. So this answer is the curl of our vector, and I can see that there is I cap, j cap and k cap present here, which indicates that this answer is a vector. So all the three things we studied today, we proved in terms of the problems. Okay, and the results justify whatever we studied at the beginning of today's class.